Hello, in this video I'm going to give some background to Christiaan Huygens, the Dutch mathematician, physicist, engineer, astronomer, who, really I think he should be better known than he is. I know he's quite a famous name, but considering his considerable achievements in multiple disciplines, I kind of feel as though this guy should be even more famous. So he was born in The Hague in 1629. His mother died when he was only 8. He was homeschooled. His father was quite well to do. They were quite a rich family. His father was a diplomat and he was an advisor to the Dutch royal family, as well as being a poet and a musician. So they had enough money for some, quality homeschooling. His father was also personally acquainted with the likes of Galileo, Descartes, Mersenne. He corresponded with many European intellectuals, just as part of a sort of a side part of his day-to-day job advising royalty. And Christiaan Huygens, he excelled particularly in geometry during his homeschooling. He was dubbed as being the new Archimedes, that he was so good at geometry. He had little interest really in following his father's footsteps as a diplomat. And this was really confirmed. By the time, what was it, in 1650, the House of Orange, who were the royal family in Holland at the time, they were removed from power. So his father's influence waned a little bit. And for those in the UK like myself, the House of Orange is most notably associated with William III, who with Mary, who was the daughter of James II, James the seventh of Scotland. They ushered in the Glorious Revolution in 1688 that set up the parliamentary rule that we have had ever since in this country. And on the continent, William had been leading the resistance to Louis XIV of France before that. So they were a very powerful, influential family, but they lost power in 1650. At least for a time. So the influence of Huygens Senior was much reduced. Now, as was common at the time, much of Huygens' early work is recorded in his personal correspondence, so in letters that he sent to other people, rather than, they weren't publishing papers and books and such like at the extent that they do nowadays. They were writing letters to each other. He wrote letters to Mersenne, who's a friend of his father's. And in such letters, he included, age 17, he did a demonstration that a hanging chain, if you just leave a chain, you connect it at two ends with a bit of slack, then what shape is it hanging in? There was an assumption that it was hanging in the shape of a parabola, but he demonstrated age 17 that it wasn't a parabola. He later coined the term catenary for it. He coined that term in 1690 when he was writing to Leibniz. So again, another example of this sort of correspondence that was going on at the time, in letters. And in the 1650s, he switched much more to science than just his geometry. And he did some work on mechanics. He showed that a lot of Descartes' ideas and work on collisions were actually wrong. So he created new formulations around mechanics, things like the center of gravity of a closed system remaining in constant motion. And this is something that I've gone through in some of my other videos, that if you've got a closed system, a whole load of things that say happening inside a space without any external influence at all, okay, you can describe individual collisions and motions of all of the objects inside this space, but if you look at the motion of the center of gravity of this closed system, that just stays in constant motion. Unless there's some external force, in which case it's not a closed system anymore. That's what happens with that center of gravity. He also derived the centripetal acceleration or centripetal force formula, the stuff that we derive at A level. And I went through that in one of the earlier videos. So Huygens came up with that. In astronomy, he was the first person to identify Titan as being a moon of Saturn. That was in 1655. He also explained what Saturn's rings were. People had obviously observed them and they'd seen these rings, but it's one thing to see them and it's another thing to actually explain what they are. So Huygens did that also in the late 1650s. And in 1657, he invented the pendulum clock. And this was partly driven by this motivation to solve the problem of longitude, as something else which I've spoken about in previous videos, where it's quite easy to work out latitude because you can look at things like the pole star and things like that, know what latitude you're at. But working out longitude, you really need an accurate clock, which is why you've got wonky maps. If you look at old maps, because they're trying to work out where they are based on how far they've traveled. If you're going, say, round the equator or something like that, you haven't got an obvious measure. You can't use something like the pole star because that's just telling you how far up or down you are in latitude. It doesn't tell you the longitude. You need time for that. So motivated by this, he came up with his pendulum clock. But as anyone who's tried to use a pendulum clock on a boat will tell you, the motion of the sea is not great for pendulum motion. So it didn't really help. But in terms of accuracy of a clock, I mean, before the pendulum, really people were using these sort of, the spring and ticking cog type mechanisms. And Huygens, his clocks, they were improving accuracy from, say, 15 minutes a day going out of time to 15 seconds a day going out of time. So it was a massive improvement. I mean, he did a major work based on oscillations in clocks, the horologium oscillatorium or something like that. Oscillatorium, horologium oscillatorium. Okay, I've got my O and L kind of merged in there. Horologium oscillatorium. That was in 1673. And I mean, you can view that as being the first proper work of mechanics as we view it nowadays, as in he's taken a physical problem, idealized it, created some kind of model of that physical problem, and then analyzed it mathematically. And it was inside there that that was the first derivation of the 2 pi root L over G for the period of oscillation of a pendulum. So from that point of view, I mean, he could be described as the first sort of, theoretical physicist, that he was abstracting out into a mathematical model of a real world scenario, rather than just trying to spot trends in empirical observations. I mean, that's still no mean feat, but he was abstracting out an extra mathematical level there. I mean, staying in optics, which is what he's probably most famous for now, and why I've put him in this section, he's creating his own lenses. He was tackling aberration. He tried to explain what was going on with geometrical optics. So using his skills in geometry, looking at the path that light was taking through various media and trying to describe what was going on. And this is where, this leads into the Huygens-Fresnel principle, where they were looking at light being a spherical, sort of a propagating spherical wavefront. So you think of some point where light is starting out from, you've got these spheres that are propagating outwards in all directions. So this is going into the screen and out the screen as well. And you can treat each point on this sphere as a new point source of light. And then you think, okay, for each one of these point sources, these are all propagating outwards. Okay, just draw a few of them on. And then the common tangent of all of these new individual little point sources will be the new wavefront. So you draw a common tangent in, which is just going to keep propagating that sphere outwards. So that was his description. I know it's not a full explanation of actually what's happening, which of course is described nowadays in quantum theory, quantum field theory, and quantum electrodynamics and such like. But it was a way of visualizing something that was going on. It was talking about a wave nature to light. I mean, admittedly, this did assume to a large extent that light was going to be a longitudinal wave in, in some kind of elastic medium, operating a bit like sound. Which was getting into this idea of there being an ether, this luminiferous ether that people were looking for throughout the 18th, 19th century. But yeah, I mean, it was a new way of describing things that was pretty accurate. I mean, people initially sided with Newton's his corpuscle theory, his particle theory of light. But then, of course, in 1801, you had Thomas Young with his double slit experiment, and then the wave theories of light really started getting favourable attention again. And this is where Huygens came back in popularity, and his work got revisited. So, I mean, this is a guy, as I said at the start, he's covered an enormous amount of areas of science here. I mean, he's gone through maths, he's gone through engineering, astronomy, physics. You know, we've got optics, we've got mechanics, got all of this going on. I mean, in terms of breadth of impact, I mean, he seems to be seriously getting up near to the level of someone like Newton. I mean, I know Newton has had a bigger impact. It could probably be argued, you know, through his mechanics and such like. But yeah, I mean, Huygens really, you can see he's a contemporary of Newton. So yeah, I feel as though this guy really should be better known in terms of his total contribution. It's not like he's a nobody and no one's heard of him, but he's quite often spoken about quite narrowly just in terms of optics rather than the wider contribution that he had to maths and science. So yeah, definitely a guy to know a lot more about.